All right, good morning. We have a little smaller class today. How's everyone doing? So you should have the homework, assignment, project, the next ones going around. The homework assignment is from the first chapter for this module, and homework project, you'll write a memory simulator. Some other stuff in the actual paging and stuff, we'll go through them later in the class, right? But read through them right now to see what is required and stuff. It's due right after the spring break, and turns out I didn't calculate the number of hours between now and spring break, so the next exam is actually after spring break, not right before spring break. I had one too many days between now and the exam, right? So it's actually the day after spring break. So the day after spring break, we'll have the midterm and the projects due. Actually, I didn't want to push it after spring break because it's probably taking time from spring break. But so I think that somebody had a conflict with the day before spring break. Now, we'll see if anybody has a conflict. If they do, come and talk to me and we can work something out, right? So now we move on to the next module. So far we spent all the course on looking at processor, how to assign processors in terms of the abstractions of process and threads, how to schedule process or a thread on the machines, and what happens when processors try to synchronize or share variables. Right? That's the component we looked at. So the next two modules are, we look at other resources in the system, and the next one is the memory, which is what we're going to focus on for this module. The next one is on storage, right? And these two are just as important in getting your program to work. So that's the focus of this particular module, right? And it requires some knowledge of what happens in the hardware, because a lot of the tricks that we're going to do at this level would require hardware support. Essentially, what we're trying to do is the same thing that we did with the CPU. If you don't have enough CPUs, how do you, the process of scheduling basically is you didn't have enough CPU, so you kind of made it look like you have more CPU by scheduling, by moving stuff in and out, and you're going to try to do the same thing for memory. If you don't have enough memory to hold all the programs that you ever want to do, how do we move these things around so that it looks like you have enough memory to make progress, right? And that's sort of the high-level view of what we're trying to do, right? So, and the reason why we don't have enough memory or enough of the good memory is cost, and that goes into the architecture aspects of it. So one of the things that you learn in architecture is there are these memory hierarchies. There are some memory which are really fast and super expensive, and others which are really big but not that expensive, right? So going from the CPU, you have registers which are extremely fast and very expensive. And then you go into various levels of cache, L1, L2, L3, what have you. And then you have your main memory. And then you have your backing store, hard disk, or whatever, right? And if you go in that spectrum, hard disk are the cheapest and the slowest. And registers are the fastest and the most expensive. And on-chip cache comes in next, and so on, right? So if you want performance, you want the stuff to be closer to the CPU, right? But you move it to the slower ones to make it look like you have more than what you have, right? And that's essentially what you're trying to do, right? So the hardware dictates that something is fast and something is slow, and from the OS, we want to make sure that everything that you're working on is as close to the CPU as possible, because essentially it has to be close to the CPU for the CPU to actually use it, right? If it's on the hard disk, then we can't use it at all. If it moves in the main memory, then the processor can start to use it, right? But it essentially has to move everything into its cache before it really uses it, right? So that's the hardware component which affects what we are trying to do, right? So so today mostly I'm going to introduce lots of terms, lots of little disparate stuff, and I think it'll come into more focus as we go to the next few lectures, right? So the first thing we want to look at is what happens when you write a program. When you write a program in C or something, how does it, what kind of things it goes through, right? You compile a program and you create an object file, right? You create some kind of a thing, what you call a program, in edit out or something. And the problem is, how do you take that and put it into, stick it into main memory somewhere and make it run, right? So essentially, if you knew exactly what the memory is going to be looking like, when you do a compilation, how many of you actually taking the compiler course concurrently? Okay, so it's a more of a senior level class, and so essentially when you take the course, right, you take your high level C program statements, and then you want to translate that into machine language instructions which can work on processes. And when you take your variable in your C program and put it into memory, right, you can do it at compile time, figure out where the memory should be. So your compiler can lay out how the memory should look like, put the processes and put the memories and everything where they should finally stay, and compile this program, right? And that's the simplest way of doing things, because it basically works for that particular machine and no other machine, because it needs the same amount of memory to be exactly where they are, the processes to be where they should be, right? That's the negative side of it. The positive side is it's very simple, right? The machine can run it very easily, and as we'll see, the later half, the other techniques are more flexible, but they also require more from the hardware, right? If your hardware, if all it does is lets you run programs from main memory at some location, compiling it in and creating executable which can run on the particular machine as it is one way to go, right? But what you would really like to do is have the flexibility to have you write the program, but load it into a different location, to make it run in a different location. And you can either do it while you start the program or when you're running the program. And that's essentially the next two options, right? So here in the second one, you write the program, right? And you create what is called relocatable code. Essentially, instead of allocating some variable into some memory location, you allocate it as an offset from something, right? So you can say from the start of the program, my memory for variable A would be at byte 1000, rather than saying it'll be at byte 2000 or something, right? So you say something as a start from a known offset, and that's part of what you can do with the relocatable code. So when we finally decide to load them, right, we decide where we're going to put this process in the main memory and figure out what's the start of these things, and essentially relocate it on the fly. So you can actually say all the variables accessed from the start plus 1000, and the OS would initialize start to something that it chooses and let it go, right? So with that model, once you start this program with this particular address, it's stuck there. So it can't move anywhere at all. The next option is to be able to move this dynamically, to be able to change these variables dynamically, right? So the way you look at it, if you look at the memory as a long chunk, right? When you write the program, you can say in assembly instruction, right? Load 0x 4350, right? Which is basically the first option, which says that load whatever is in address 50 into some register, right? And this program can only run if this value is true, right? You can't really change anything after you've compiled it. Whereas in the second model, you write the code to say, you define something called start, right? So essentially, it's something like start of 1000, right? Essentially, you don't know what start is, and whatever start is, it'll be 1000 bytes after that. So the OS can put the data in some section here, it can figure out what start should be and initialize start to what it wants to be. So every access would now have to add whatever your program gave plus the start, which the OS set, to figure out what address things should be, right? And of course, you need hardware support for that, because otherwise the program is going to slow down a lot, right? Every instruction has to add this constant. So you have to take the start and add something, right? So if you don't do it in hardware, and if you're trying to do it in software, then your program is going to run half the speed, right? So the third option is to make this dynamic, right? So maybe put that in a certain register. So every time you run a program, the OS will take whatever address you call and add it to contents of some other register to get the effective address of where things should be, and lets it go, right? And you have to have hardware support for making it this possible, right? So the first option, you don't need hardware support. Hardware already knows how to execute instructions. But for the next two, you need hardware to be able to add these things for every instruction. And most modern hardware does that. So that's not a problem for most of the general purpose operating systems, right? Most of the general purpose hardware. It's maybe not true for small things like cell phones and stuff. So is there a reason why we would consider compile time loading at all? I think I gave the answer somewhere here there, but yeah.
If you're making something for a certain device, like a cell phone, and you have the same memory every time you turn it on, so you don't really care. It would be faster just to compile it that way, more reliable.
Yeah. So mostly, if you have a device like a cell phone, you don't tend to change a whole lot, right? It's manufactured the same way, and you don't. And the cell phones also want to keep the cost down. So the other two requires that every instruction has to add something and stuff, and that adds to hardware cost. So if you're building something for a cell phone, even though it's not really true for the most modern cell phones, they tend to run Java and smartphones and stuff. But essentially, that's the idea, right? So, but the more you add, the more flexibility it has, and also now the OS has to keep track of all these registers and stuff. It's no longer the case that you take a program and all the OS has to do is load it up and then let it go, right? Here it has to load it up. In the second option, it has to figure out where to place you and give you the value of start. In the third option, every time it decides to schedule to run you, it has to make sure that all the appropriate registers, appropriate stuff is current, right? Otherwise, you won't be able to make progress. Which essentially brings up how things are loaded into memory, right? So one of the things I mentioned before was you may not have all the memory that you would want to run all your programs. So we are trying to multiplex it just like we are doing for the CPU. We're trying to make sure that many of them can use the same resources that you would like. So these are two techniques which are there to save on how much memory footprint your process has. Right? So the first one is dynamic loading, right? Which essentially says that the simplest way to load a program is to load it entire stuff into memory somewhere and make it run, right? So when you start a program called a.out, you'll load all the stuff that the program would ever want into main memory and let your process go. And it's simpler because it does all the work upfront once, loads the whole thing, and lets it go. So the simplest thing would be to load everything, have it compile at memory time, and everything is good to go. But usually most programs have lots of code which are never used, right? You have error conditions, help pages, and what have you, which are never really called. So there's no point in loading everything if you're not going to use them. So the first optimization that most operating systems do is doing what is called dynamic loading, right? So the OS now has to keep track, so it doesn't load everything. It only loads some things, and if you try to do something on memory that you don't really have, then things happen and it loads them, right? We will see how precisely that happens as we move along. But the idea essentially is when you start, you just load the minimal set of stuff you need, and every time you call an instruction, you call a function or something, if it's not in main memory, you get a trap, and essentially the trap code brings it in, right? So you amortize the cost as you use them. So when the startup time is simpler and easier, while during the execution time, your program may stop for a moment while it tries to load its next objects, right? So essentially, this saves you from, so if you think of your Microsoft Word, right? Your Word executable has, it can do all the stuff that you may not really want in a particular session. So when you start your program, it brings in just enough to show up the screen. So if you start your grammar checker or spell checker, then those are brought in as needed. So this way, you can actually run two processes and have them both stay in memory by keeping just the working set. We'll get to that notion a little bit later, but essentially, you're trying to keep only the stuff that is actively being used in memory and leaving the rest on hard disk, right? So your program is not fully loaded, only what is absolutely needed right now is loaded, so you get to run more processes than you could otherwise, right? So the next option is dynamic linking. Both of these are sort of compiler technologies, and it's a mixture of where these two happen, right? With dynamic linking, right, the observation is typically programs compile against the same library, right? So you're going to have code reuse between different programs. If you're calling libc, right, you can assume that most processors would call the C library. So you're going to have the same copy of the C library across multiple processes. So if you compile the libraries into your program, you're going to essentially have a much larger program, right, where the same piece of code is shared among multiple processes, right? Does that make sense? So if you imagine this is your process, right, this is the code that you actually wrote, and you may use common libraries that you link with other standard libraries, like your libc, your X Windows code, or Windows code, or what have you, right? So if you have another process, it's going to have the same thing. It's going to have its own code, but some component of the libraries are shared, right? You can't just reuse them as they are, because your compiler may load them into different locations. Your compilation system may put them into different location, right? Your compiler treats this as a separate executable, so it can decide to put this library up here and this library in a different location, right? And there are protection issues and stuff. So you can't just access them as they are. What you try to do is you put a stub here, right? And that stub tries to figure out, so essentially these are loaded separately, right, into some location. And when if this comes here first, it finds out that it's not loaded, tells the operating system that this particular stuff is not loaded. The operating system will load this stuff, right, and set its registers to its relocation registers to say, whenever you use this function, use these set of addresses, right? The code is completely relocatable, so anybody can come in if you have the right set of registers. And when this process comes in, it can know that this is already loaded, so you can use it as it is, right? Some of this hardware and stuff, we'll see as we move along. But the essential idea is you load only one copy, and as long as we can protect this user from changing some of this stuff, right? Because if they do, then your program will start to work differently. Because this person modifies this program code, and this person tries to use it, and you'll have bad stuff, right? As long as you can prevent that, as long as you can prevent processes from modifying code, right, you can essentially leave these libraries as dynamically linked, and the OS would load them as they are, right? So the second way, you tend to have only one copy of the library for the entire system, and in the first way, you only load the stuff that you really need. So in the main memory, you cut down a lot on how much space you need for the programs, right? And the second one is basically your DLL, in the Windows world it's the DLL, what they call DLL. And in Unix and all, it's called shared library.so libraries, right? And there are other things which come with doing this stuff. One of the stuff is you can have multiple versions. I can update the libraries without actually recompiling the program, right? So the compiler can change this C library to a new version, and your program would now have its bugs fixed without changing anything, right? So you can look at it as a positive and say bugs can be fixed without changing a program, or a negative in terms of bugs can be added without anything happening to your program, right? But it's a standard set of stable of operations that you have in any modern operating system, right? So all these three will make sure that you have the flexibility to only load what we need, not duplicate the set of code, and be able to move stuff wherever we want. And these three abilities lets us do, all these three functionality, right? And we'll see how this will be used for the memory component too, right? So is that clear so far? So essentially, this is the sort of the flow chart of what happens when you write the program, right? And this will probably be the focus of a compiler course. So you write your program up front, you compile it, you create object files, you get .o files, right? And then you call linker or LD in Unix, which adds some of the libraries and creates a load module, right? At that time, it also links in the stuff for dynamic libraries. So when you run the program, right, the in memory version will have the program that you had and the dynamic loaded calls which are loaded, right? So using this dynamic link libraries, your program can either fast very quickly or slowly, right? So if somebody else has already loaded these functions, then it's basically a function of setting some register values and letting your program go. But the first process which has to come in has to load all the stuff and create all the structures, right? So this is one of the reasons why finding out how big your process is sort of misleading. How many of you have tried to look at how big a process is either using PS or your task manager's size thing, right? So what was your...
Yeah, it depends. Like, some things in Visual Basic you can see really easily when it loads up graphics and stuff, but sometimes it'll hide things in the swap space, and you don't really know what the OS is doing.
And somebody else raised their hand. Yeah, so you don't know which is loading, and the other stuff is when you look at your process, your process may say it's this big, right? Your PS may say your process is this big, but essentially what is in memory would be a lot smaller, right? The sum of all the process sizes would not equal to what is actually used. So in this case, this and this is being reused. So it'll look like this process is this big, this process is this big, but essentially this process is, that's not, you can only count this once, right? So if it's a common library, then almost all the processes in your system would use that, but it will show up as adding, it will show up in each process, right? So if you do a top on one of those things on a PowerPoint, right? Your PowerPoint will look fairly big, right? Your PowerPoint memory footprint will look fairly big, right? So you'll see somebody complaining and saying, like your PowerPoint is using 400 megs of memory or something, right? It's not. I mean, it's basically using 400 megs, but the 400 megs is reused with other stuff. So it's not actually using 400 megs on the memory, right? So the next concept is, so we're not looking at the compile time loading anymore. So we're trying to look at the other way of moving stuff around to have more flexibility, right? So in that world, we define a notion of a logical address and a physical address, right? So the idea here is when you write a program, and compile it and everything, we operate in logical address. We operate where the compiler can say, I started address 0 to 100,000. It doesn't have to be 10, 0 or whatever, right? But essentially, you write your program as if nothing else exists, right? And your address space that you assume the number of addresses, the number of registers and stuff, the number of addresses, memory locations, you assume to start from some location and go on to some other location, right? And your physical memory, whatever much memory you have, so if you have half a gig of memory, it starts at 0 and goes on till 512 megabyte, right? So there is an address here, right, which says that address 1, address 2, address 3, what have you, right? And your program will have address 0 to what have you, right? So this is the logical address and this is the physical address. And the OS basically does tricks with the use of the hardware to essentially map this into some area here, right? Your CPU can only work in physical address because it has to know where it is right now. So you may have loaded this particular stuff from here to here. Let's say I load it here. From your program perspective, it's going to say, I want to access address 500, right? In the physical address sense, it may translate to 3500. So your program thinks in logical addresses, which start in 0 or some known location and go up, whereas the physical machine keeps track of where things are actually located, right? So your program will never know what its real address is, and real address may keep changing, right? But your logical address is always the same, and that will remain wherever you're. So if the OS decides to move this through some mechanism, your process will not notice a difference, right? Your process will not know the difference. It won't even know that the translation is happening, right? So that's the notion of a logical and a physical address. So physical address and logical address are the same, except when they are actually running, the physical address will be different than logical address. Physical address will be where the logical address maps to on the particular machine at any particular time. So the translation essentially means that is the stuff I was talking about here, right? Your program only talks about the addresses it wants, and somebody has to add something to make it into a physical address. And the hardware unit which does that is the memory management unit, right? And you need hardware support because otherwise adding everything is very expensive. Let's see. So this is essentially how you try to do it in hardware. So your CPU creates your program creates a logical address of 346, right? Your memory management unit or some hardware would have to have some register which tells it where the program is currently loaded, and it will add whatever the program is asking with that register to figure out what the actual physical address is. And that's what goes into the memory bank to read the contents, right? So this means that every memory access for your program has to go through this addition operation, right? So if you don't do it quickly, then your process will suffer. So your MMU is an integral part of you doing this. So if you want to do this relocation facility, then everything has to happen in hardware, and right. So the hardware, so this MMU unit which would add this stuff, right? So who would set that relocation register? Right, there's a relocation register which figures out how whatever your program is asking should translate into memory addresses, right? Whose responsibility is it to set the relocation register? Yeah.
The operating system.
So, yes, the operating system has to keep track of it, right? What could go wrong if somebody else has access to setting the relocation register? Yeah.
You could run code that wasn't supposed to be executed at that time, like do kinds of buffer overflow and things like that, and just execute random code.
So essentially, you are kind of using this as some sort of a protection mechanism too, right? So from your process, all you know is these addresses, and you're accessing stuff within that address space that you're looking at, right? And in the next slide, I'll show you how you can restrict what you do within your own process, right? But if I can muck with that relocation register to say something else, then I can essentially read anything in main memory, right? I can read kernel data structures, I can read stuff, I can write stuff which I'm not supposed to be able to. So if I don't control who gets to write what, then essentially I can read all the stuff in the main memory, right? And do bad things to it. So that's a protected operation that only the operating system can write to, right? So when would the operating system update that value, update this register value to change the register value? Like once when the program starts, once when the system boots up. Yeah.
Maybe there's a context switch.
Mm-hmm. Yeah, every time your process changes, it has to remove this mapping, so the new process can have the addresses the way it wants them, right? So we'll see that there are a little bit more complications, but for now, if I have the so if I have program 2 here and program 1 here, when I do the context switch, I have to allocate the CPU to the new process, and I also have to make sure that all the memory management units are up to date with the right addresses, so they can actually continue to run, right? So when I do that, all the future translations will go to the correct addresses, not the ones that the previous process was using, right? So again, we add a number of little technologies, and we'll see how we can use them as we move through this module, right? So far, what we have done, we have figured out how to avoid loading program code where we don't have to. We delay what we have to load. We share the objects across different system libraries, right? And we kind of figured out how to move stuff or load stuff into whatever location, right? And for that to be, so the next technology would help us actually use the ability to move processes, and that's called swapping out, right? The idea is, whenever memory is becoming full, and in this case, the physical memory, right? The logical memory does not have to fill up. Whenever the physical memory fills up, which means that you actually have contents here which are useful for somebody, right? One way to make progress is to move the stuff off somewhere, right? Write it off to somewhere, and in this case, we write it to a hard disk or what have you. But essentially, since this process is not running, right, its memory footprint is not changing, so we store it somewhere else and restore something else back into here and let it go, right? So if you want a context switch from P2 to P3, right, we would write P2 into some backing store and read something, the P3 back in here, and set the MMU registers so that your process will not know any difference, and you continue to move, right? And for this to happen, you need to have a storage which is large enough. So if you have enough swap space, then I can essentially move these things back and forth. So essentially, I'm making the physical memory appear as big as my swap space, right? I can move as many of those things back and forth, and that's the notion of swapping, right? And we'll see the penalties of doing all this stuff. And so you can implement priorities this way. So if you have a priority, if you have a preemptive machine, right, I can preempt the process, move the footprint of all the memory location off to the swap space, and move the new one in, right, and let the high priority task finish. And after it's finished, roll it back out and move it forward, right? And we'll see a lot of reasons of how we can optimize and how things will be bad, right? So, as a hint, right? So, if you have, this is a program with code and this is data, right? Code is your program and data is the variables and stuff where you store. So when you're doing a swapping, right? When you're trying to move stuff off to the hard disk and bring it back, do you do different stuff for code and data, or are they the same? Can you think of any optimization here in terms of what you're trying to do, right? The idea is you need the space and you have to store them somewhere, right? Can you do something different based on whether it's code or whether it's data? Something else to take? Something you can try. Right? You have a piece of code and you have a piece of data, right? I'll give you a hint. Programs don't usually change themselves, right? It's considered bad practice for self-modifying code. You might have written it in the days of DOS, the old operating systems and stuff. But usually you're not supposed to write programs which change themselves, right? You know what I'm talking about, right? You can change your program on the fly. You can change the instructions on the fly to make it do cool stuff, and it's cool sounding, but it's a nightmare in terms of debugging, right? Your program changes on the fly, so you can do different things and what have you. Most machines do not want you to change the program on the fly, right? Which means that your program is static; it does not change. Whereas your data, for the most part, tends to change, right? You take a variable, you add something, you do some operations on it, because it's a very boring program if it doesn't change any data, right? So, can you think of doing something using that knowledge? So what would you have to do if you want to swap out data? The simpler case, right? You would have to actually write it to the hard disk because it might have been changed. So you would have to save it because you have to protect that, right? If it's code, right, we know that it's not, you can't modify it, right? So do we have to write it to a swap? Because your code actually came from a program, right? Your program is sitting here, which is where it got loaded from, right? Your hard disk has your program, and you read the program and you're running it, right? Yes.
You can just create some kind of structure in the OS to tell it to reload the program next time you want it.
Yeah, so you can actually play some games here and say, well, this particular piece of object came from some other file, so if I do want it, I can reload it from there. I don't have to store it back, right? You can actually do a lot more tricks, and we'll see some of them later on, right? If the OS can keep track of the state of the registers and stuff, state of the machine, and see if a particular memory segment was returned to, not returned to, and all those things, he can actually do different things. So if it knows that the object is somewhere else, then it does not have to write it, right? If it knows that the data item was not modified since the last time it was returned to swap, and the last item was still there, it does not have to rewrite it, right? He's trying to do all this stuff because this is much faster than your hard disk. Your hard disk is much slower than your memory, so anything that you can do to avoid this stuff would make your system go faster, right? And we'll see what happens. So one of the things I said was, you can make a program essentially look as big as your swap disk. But there's a limit to how much you can do, because if you make the swap disk to be infinite, then yes, your program will look like infinity, but it'll also take a lot of time because it's basically moving stuff back and forth, and that's called thrashing, and we'll see some of that later on, right? So there is no free lunch. I mean, all the trick we are trying to do is trying to optimize what we have. But if you want high performance, you still want to have more memory, but there are some tricks you can do to avoid moving stuff back and forth if you have to, right? And sort of this is the schematic of what you imagine as swapping. And for now, we are looking at swapping the whole process in and out. So you swap one process out and bring the next process in, and then you move forward. And we'll see that we don't have to do it all on a process basis. You can do little chunks in the middle of what exactly you're doing. Right? So the next task is, I had something like up here, and I said, process 3 should go here, process P1 should go here. When the process P2 comes in and it wants memory, what should happen, right? And you can think of it as a contiguous allocation. So if the process 2 comes in and says, I want 10 meg, right? You have to figure out if you have enough space to allocate the 10 meg, and suppose this is 8 meg and this is 2 meg, right? And so if it asks for 10 meg, either you don't have the right thing, in which case you may have to swap things back and forth, or you may have to move this stuff around, so you can add this and this to create 10 meg, right? So the problem now is, when the process comes in and it wants more memory, how do you allocate them, right? You allocate them as, and it really helps that we have relocation registers, because then we can actually allocate them wherever we want and move them around later, right? So the notion that I can move these two here and add this and this to create a 10 meg partition depends on the facility for me to move. And the reason I can move is all the addresses are in logical address space, and everything is going through the relocation address. So if I can set the right relocation addresses, then I can essentially move. The processors won't know a difference. You'll still notice a slowdown while you're doing this, because none of this comes free, right? So if you decide to move this up here, you have to stop the whole system and move the contents here, copy everything from here to here, set the appropriate set of registers and stuff. But from a functionality perspective, all this can happen without anybody being the wiser, right? You'll still see a performance hit, but not a functionality change. So we kind of talked about all this stuff, and so essentially you also have a notion of a base and a limit register, right? So within a process, you set a notion, within a particular process, you set a notion of a base and a limit register, which says how far the process can access without something's happening, right? So your process, a single process may actually span from 25,600 to 88,000, right? Depending on how we use these two bound registers, which is the focus later on. You can do different things. So in the simplest case, if you set the bounds, the base to be 25,600 and the limit to be 88,000, it says that if you try to access anything outside of this, then something should happen. The OS should be notified or something. In the more complicated case, you can have this little bit pieces up here. So essentially what you're trying to do is every memory access now you want to see if the address you're accessing falls within these two limits. So you're trying to do is the address more than base and less than base plus limit, or less than the limit register, whichever way you have it, right? So if the logical address that you're looking for is between these two limits, then you do the relocation part, right? So essentially you take your address to see if they are between these two parts. If they are not, right, then there is something wrong. And depending on where you get the trap, OS can do a lot of stuff. So to give you a hint, if the address that you're looking at is below 25,600, right, that means you're trying to access memory that was not allocated to you, right? So in that case, you should get some kind of a stuff to the process, and usually you get a segmentation fault. And usually you get a segmentation fault. And in Unix, if you try to access something which is not part of your program, you get a segmentation fault and your process is killed, right? So if you try to access anything above that or below this, he'll give you a fault. But if you try to access anything within here in unintended ways, then that's fine, right? Because the OS is only doing a sanity check, right? So that's one of the uses. The other use is if the OS can move part of the stuff out to disk, right? It can say I have allocated you from 25,600 to 88,000, but for now I can only guarantee that 3004 to 2090 is there in main memory. If you try to access anything beyond that, right, I need to be notified. If I'm notified, then I can actually dynamically throw some other, figure out some pages, put them into the swap, move something back, so let you continue, right? You're asking for a page which rightfully belongs to you, but the OS took it away because it had to multiplex these things, right? So the notions of base and limit can be used for protecting the process from messing with something that it should not have, or for the OS to try to multiplex these things, right? I introduced a whole bunch of concepts, and throughout the course we'll use more of this into the little things we talked about, right? So bear with me for now, right? So this is the notion. So the hardware on every axis now has to figure out if it's within some bounds. If it's not, it'll do a trap, let the OS know what to do. The OS can figure out what it does depending on what it's trying to do, right? And after that, it has to add whatever address that you have with whatever is in the relocation register to actually know the physical address of where things are, right? So this complicates things a lot. I mean, it's no longer a simple, I want address, I go to my memory and read them. It has to go through these sanity checks and stuff, all of which have to happen in hardware, because otherwise every instruction will slow down, right? So that's why your MMU does this stuff. But the OS gets a little bit more complicated because it's trying to play these games to swap things in and out. I'm going to stop at this point and we can continue with the